All right, welcome to part 2 of finding volumes using cross-sectional areas of geometric shapes. In the first video, what we did is we kind of talked about how you could take the area of a geometric shape and find an infinite number of them using an accumulation technique or integration to find the volume of a three-dimensional shape. Well, now what we're going to be doing is we're going to be applying those so we can actually find some volumes. So let's take a look at the first example here. Find the volume of the solid whose base is bounded by the function y is equal to the square root of x, a vertical line x is equal to 4, and the x-axis. Now what it's telling us is that each cross-sectional shape is going to be a square, and we are looking at something perpendicular to the x-axis, meaning that we want things solved in terms of y, which is what I have here. Now the function itself, it's not strictly necessary to view it, but I'm going to go ahead and take a look here so we can see, because a lot of times having this visual reference will be helpful for identifying the interval of the function. So let's go ahead and graph the square root function. It's just going to be kind of something like that. Here, where we have the line x is equal to 4, that point right there is going to be 4, 0, and it would intersect here at 4, 2. And what we're going to be looking for here is the graph, because we're doing it in terms of y, where it's perpendicular to the x-axis, this bit right here is going to make up the interval. So our interval in this case is going to be from 0 to 4. Now, to find the area of the shape, we look at it, the function in terms of y, which we already have, and the area of the square, as you recall, is side squared. So when I substitute the side for the function, I'm going to get the square root of x squared. So the area in this case will be just written in terms of x. All right, now we can, we know essentially what the area is going to be. That's what we need to substitute into our integrand. So now I'm going to say volume is going to be equal to the definite integral from 0 to 4 of x dx. So the function is already, or the integrand is already about as simplified as it can get. So we go ahead and take the antiderivative here, and this will be 1/2 x squared for the antiderivative, and we're evaluating it from 0 to 4. So I'm going to have the 1/2 pulled out as a constant, and then we would just substitute the 4 and the 0 with our fundamental theorem of calculus, so that'll be 4 squared minus 0 squared. And 4 squared, 16, minus 0 is still 16, so half of 16 says the volume in this case will be 8. So now let's move on to the next example. This one's going to be a little bit more challenging. Find the volume of the solid whose base is bounded by a circle. So we give us the equation of a circle here. Because 9 is the last number, we know that the radius is going to be equal to a 3. With the indicated cross sections perpendicular to the x-axis, so we know again we're solving things in terms of y. And here we have isosceles right triangles, where the hypotenuse is going to be the base of the triangle. So again, I'm going to kind of take a picture here of what the graph would kind of look like. So we have a circle here. We'll just say that this has a radius of 3. So at this point here, this would be 3 and 0. And this would be here, -3 and 0. And here we have one y section, and here we have another y section. So that's going to change the way our graph or our base is going to look here for the triangle. So that y segment is that isosceles triangle, kind of imagine that, shape here, that is going across the entire diameter. So essentially what we have, oops, and I don't want to write, I want to, come on, let me turn, oh, rotate, rotate, there we go. Oh, when plane comes together. So when we're looking at the triangle here, here's our altitude here. So this bit here is a y, and this bit here is another y, one for the, from the origin up and one from the origin down. And because this is an isosceles right triangle, the altitude is going to be the same thing. That's also going to be a y. So let me pick another color here, and we'll look at the area. Area of the triangle being 1/2 times the base times the height. Well, if I solve the equation, let's take a look at the circle. If I solve that in terms of y, that's going to be y is equal to the square root of 9 minus x squared. So here I'm going to get 1/2 times 2, so the overall base is going to be 2 square root of 9 minus x squared times another square root of 9 minus x squared. So the 2 and the 1/2 simplify to be 1, and the square root of 9 minus x squared times the square root of 9 minus x squared will just be 9 minus x squared. Now, in this case, the interval, what we're looking at, the interval is, let me pick another color here for the interval. Did I get my, no, give me my blue. Okay, so the interval in this case is going to be from this x point all the way to this x point. So the interval is going to be from -3 to a +3. But personally, if I can avoid that lower bound being a negative number, I'm going to, simply because I want to avoid working with negatives. So I'm going to look at the interval in this case to just be along this bit of the x-axis here, and then I'll simply double what my integration will be for the symmetrical nature of the circle. We can find the volume of 1 and then double it to get the volume of the whole thing. So that's where we're going to be at now. I'm going to say the volume is going to be equal to 2 definite integrals from 0 to a +3. And we have the y value, the area, to be 9 minus x squared dx. Now the integrand itself is already simplified. It can't really get any more simple than what it is, so we can go ahead and take the antiderivative. So we'll go for 9x minus 1/3 x cubed, and we're evaluating it from 0 to a +3. So this give me 2 times, oops, not 2, I got 2 on the brain, times 9 times 3 minus 1/3 times 3 cubed. And the reason why I like having 0 to be my lower bound is because anywhere I substitute 0 into the expression, it simplifies to just be a 0. That's why we want to, it's easier to multiply the expression by 2 than plug in that -3 with our fundamental theorem. But anyway, moving on. Here I'm going to get 27 and then minus 9. Oops, and I don't want to, let's keep with the brackets here. Oh, come on, turn the pin back on. Just keep with the brackets. So here this is going to give me Essentially, 27 minus 9 is 18, so 2 times 18 gives me an area, I'm sorry, a volume of 18 cubic units, whatever that happens. Oops, nope, I'm way off. This becomes, oh, okay, let's see if I can do this correctly here. This becomes 18, and 2 times 18 gives me 36 cubic units for my volume. Now I have a happy little answer. All right, let's try and get one more here in this video before we pause and try to go on to the next one. All right, we're already about 10 minutes, so I'll try and be quick. So here let R be a region bounded by the graph, x equals y squared and x equals 9. Find the volume of the solid that has R as its base. If every cross-sectional plane is perpendicular to the x-axis, and it is a semicircle. So again, we're perpendicular to the x-axis, so we want things in terms of y, and the semicircle tells us the equation that we're going to be looking at. Now let's go ahead and look at what the function will be if we graph them. So we have x and y. Now the first bit that we're going to see, and let's go ahead and do this one here in green. X is equal to y squared, that's kind of a sideways parabola that kind of goes like that. It's just like the quadratic parent function rotated a negative 90 degrees around the origin, so it kind of opens to the right like that. And then we'll say, let's do this in purple. So we'll just kind of arbitrarily say that this is where x is equal to 9. And so this would be at 9, 0. So this point would here be 9 and negative 3. This point here would be at 9, positive 3. And so again, this bit right here would be 1y, and this bit right here would be 1y. And I know I didn't quite draw them symmetrical, but you get the idea. That's basically what it should look like. So in this case, we're going to look at y is going to be equal to r. Or I'm sorry, I don't want a capital R here. I want a lowercase r because we're going to be talking about the radius. So in this case, we want to solve the equation in terms of y. So right now we have y squared is, and let me go ahead and do this in green since I graphed the sideways parabola in green. Go away. So right now I have y squared is equal to x. So that means y will be equal to the square root of x. And the area of a semicircle is 1/2 pi times the radius squared. Well, in this case, the radius squared is going to be whatever we have for y. So I can say r is equal to the square root of x. So this will give us 1/2 pi times the square root of x squared. And that would simplify to be 1/2 x times pi, or pi over 2 times x, however, depending on however you wanted to look at it. So that's the area of the semicircle shape that we're going to be looking at for this particular function. So now we're going to take the volume here, and I'm going to just pause it for one quick second because there's a noise here. Give me one quick second. Oh, sorry about that. My dogs were getting rambunctious, so I had to kind of quiet them down. So looking at the, let's see, let's pick another color here. Let's just go ahead and do the work here in black. Now in this case, we're going to be looking at the volume is going to be equal to the definite integral, and this is the one thing that I didn't identify. The interval itself is going to be along the x-axis, and probably black on black isn't going to work here. Let's do yellow. Here, the interval is this bit right here, only along the x-axis. So from the origin here to this point here, the interval is going to be from 0 to 9. And we have the 1/2 x times pi times dx. Now what I'm going to do here is I'm going to go ahead and pull out the constants. I have 1/2 and pi as constants, so I'm going to go ahead and pull those out of the integral from 0 to 9, and that's just going to leave me x dx. And this is what I need to take as my antiderivative. So here we have 1/2 times pi, and the antiderivative in this case is going to be 1/2 x squared, evaluated from 0 to 9. 0 to 9, that looked like a 2. And so here, now we can pull out the other 1/2 if you would like. Pull out the other 1/2, and that'll give us, let's just simplify it and just say pi over 4 instead of 1/4 pi. And now we can substitute the 9 for the x. Oops, and that should be 9 squared minus 0 squared for the lower bound. So we're going to say pi over 4 times 81. And so in this case, they don't simplify 81 over 4, so that would just be 81 pi over 4 for our volume. We're going to go ahead and pause it here for this one. We don't want the videos to be excessively long, but thanks for watching. There's going to be one more video on volumes of cross-sectional shapes. Thanks for watching, ladies and gentlemen. Take care.